All right, class, welcome to chapter 2. So in chapter 1, we've learned how to take derivatives. What does it mean to find the derivative of a function? And now we're going to put those derivatives furthermore to good use. So the derivative of a function gave us the slope of the tangent line to the graph of that function at that point, which in turn explained to us what's the instantaneous rate of change in that function at that point, right? So where's the function heading at that point in time? So as I said, we're going to put derivatives further on to good use, and that's for graphing functions. So I'm going to graph a function for you that you might have seen before. So this section specifically would be concentrating on polynomial functions. So a polynomial function you have learned about them in college algebra. So for example, a polynomial function has the form some number times x to some kind of power plus some other kind of number times x to maybe one less power than that. So don't be too scared, but that's really how you wrote polynomials in college algebra as well. We don't know what the highest power of this function is. Maybe it's 3, maybe it's 7, but whatever it is, right, we don't want to go a, b, c and then run out of letters. These are just the coefficients of those terms. So point is, we've taken plenty derivatives of polynomial functions. I'm actually trying to look back really quick and give you one, but we are going to deal, and I'm just going to find it in 1 second, hold on, just trying to show you. Here it is. We've done plenty of polynomial function. That's a polynomial function for you, right? Some x to some kind of exponent times a coefficient and so on, right? And the point is, those exponents had to be nice whole number, positive integers, in other words. So no fractional exponents, in other words, no radicals, no negative exponents, in other words, no rational functions, or no fractions. But what you've learned about polynomial functions, and I know because I've taught many times college algebra, is that when you wanted to graph these functions, the one thing you try to do is you try to find the intercepts, yes? So you set this equal to 0. Sometimes, sure, if it's a quadratic or a linear, it was easy to find. But you've had to go through the car rule of signs, rational zeros, so on and so on. Let's say you found those intercepts, right? The crosses through these points, yes? The other thing is you looked at what the end behavior of the graph is, and we're going to do some examples. The end behavior was told to you by this highest exponent. And again, if you want to review that chapter out of college algebra, please do so. Strongly recommend it. But you know about where that graph is starting. Let's say it's starting here. And let's say it's ending here. And then you weave it through these intercepts, right? So the other really important fact about polynomial functions is that their graphs are smooth, continuous curves. So what does that mean? Well, we already know what it means to be continuous, right? There's going to be no gaps, no holes, no jumps into the graph. Smooth basically means no corners either. So it doesn't come to a sharp corner. So in other words, the graph of such a function, let me draw it in red again, might be like this. Goes through, and then I'm going to have to come down here. So the point is it's going to turn. But we don't know, and that's what you were told, hopefully, in college algebra, that we don't know where this graph is turning. So what I'm hinting to you is that finally it's time to learn about that. So you didn't know how high up could you go before you turn the graph back down to come here. and it's coming, has to cross through this point we've said. And again, does it turn and cross here, or does it keep going? Where does it turn? Yes, before it nicely comes back here. Ooh, I made it end here. So then I can't cross because I can't cross again, so it's bouncing off. You've learned those things as well. So again, I didn't graph a specific polynomial function, but I could definitely tell you that looks like the graph of one, okay? So the one thing we didn't know is where those turning points in the graph are, right? How much do I have to go before I come back down? And finally, that's the time for it. So by the way, we have names for these turning points. They're called local relative values. They're called local maximums and local minimums. So what do I mean by a local maximum and local minimum? Local means in its vicinity. So basically a local or a relative, depends on the textbook. I like to use the word local. A local maximum at a point is occurring at a point if the function value at that point is greater than or equal to the function values of any other x near a. That means what? Right here, and it's quite clear what a local max should be looking like. What does it mean? It doesn't mean overall looking at the whole graph. Locally, yes. If I zoom in to this point here, what do I see? That for this point here, the function value, right, is higher than the function values near it, right? So it's the highest y value, local max, right? Is there another local max in this corner? Yes. Or in this graph? Yes. Are there any minimums? Definitely. Right here, there's a local min, right? Basically a turning point. And right here, there's a local min. So let me ask you this question. Is this a local minimum point? The answer is no. Why not? This is not where it's stopping. The arrow suggests that actually this is going to go down, right? Lower and lower and lower. The same thing here. This is not a maximum. Why? The graph is not stopping there. It really is stretching on, right? We just got tired of drawing it. Okay, so you understand what a local min or a maximum is. Next thing is what's a global or an absolute max or an absolute min. So what do you think the difference between a local, and by the way, my favorite of the two is absolute. So what's the difference between a local maximum and a global or an absolute maximum? Let's look at these. Is there an absolute maximum in this function? Absolute means the highest point on this graph. So even though we have some maximums in their area, that looks like a maximum, right? There is no highest point on the graph, period. Why? Because this graph here is stretching on forever and it goes up to a positive infinity, yes? Is there an absolute lowest point in this graph? No. The same answer. Why? Because this graph is going to keep on going down, right? There will be no lowest point. So this is not an absolute min, if you were wondering. The reason for it, because we have lower points than it. So what's an absolute? You have an absolute maximum at a point A if the function value at A is greater than or equal to the function values for all x's in the domain of f. What does it mean in the domain? Alongside the whole graph, all the way from left to right. Yes? So here is another graph for you. I put them all up there. This time, oh, I shouldn't have put the arrows. The graph was meant to stop. And how did I know that the graph was meant to stop? Because this is an absolute maximum. That means this wasn't going to stretch any further, right? So if you have a piece of a graph, maybe it's the full on, right? From here to there, what do you see? It's a lowest. Local min basically is a point at which the what? The graph is turning up, right? There's another local min, there's another local min. These are local maximums, right? So in their area, there are the highest point, right? That they could be. And now looking on the whole graph, again, started here, ended here. There were no arrows, my bad. Is there a highest point on this graph? Yes, that's your absolute max. Is there a lowest point on this graph? Yes, right here, that's your absolute min, right? So, apparently, that's what we will be able to find in this section. The next question is how. So as you see right here, right, we already have some tools on graphing polynomial functions. Again, these are not the only ones that we're going to be graphing, but we're starting with these because they're the easiest ones to graph. So I was saying my graph is coming. I already have the tools of finding intercepts, right, where it's crossing or touching the x-axis. But I don't know how much, just to make it cross through here to here. I could have kept on going. I could have made this go just like that, pretty flat. So how do I know how far do I have to go before it's turning? So the key point, it seems like we should be able to find these local mins and maximums, right? And how are we going to find that? Okay, let's move on to the next page. I already have an idea. I'm drawing another graph for you. And what we're trying to do is finding these maximums and minimums of functions. Absolute or local, it doesn't matter. By the way, we'll start with the local ones, and then we'll decide if they are also the absolute. So of all the local points, is one that's the absolute lowest of them all. Okay, so let's see right here. Let's see if we can list them. Which ones are local mins? At which of these points do we have a local minimum value? Okay, so if you wrote down and you guessed what? A, E, and H, you would be correct. Yes, A is a turning point, E is a turning point, yes, and H is a turning point. That's the lowest. Which ones are local maximums? Well, which ones are turning the other way? So I'll say C, and I'll say F, and that's it. Okay. So I know there's a B here and a D and a G. What they will do, well, we'll see actually in section 2.3. So I'm going to use the same graph, come back to the same graph, and we'll learn more facts about this graph. So these points are important, actually B and G only, not D, but we'll come back to them. But of these, that's a maximum, that's a maximum. I'll get back to it in a minute. Which one's the absolute max? And again, no arrows, so the graph starts here, ends here. Is there an absolute max? And you see I'm already starting to write less. Is there a highest point on this graph? Yes, that would be C. Is there an absolute min? Yes, that would be H. Okay. All right, so we at least have an idea of what it means to be a local max min, what it means to be an absolute max min. Looking at a graph. Obviously, we will start with functions. What do I do about this, right? How am I even going to get there? Now, let's see what's so special about these points A, E, and H, and also C and F. So all these points that I've listed here for you, mins or maximums, let's see what happens. Now, it's about derivatives. So let's look at the point A. Can we draw the tangent line, which is again, the derivative is the slope of the tangent line. So can we draw a tangent line to the graph at A? Sure, it looks to me like it's going to have to be horizontal, right? Sitting right under there. Can we draw a tangent line at C? Yes. Again, looks to me like it's going to be horizontal. All right. What about F? Where is the tangent line? Tangent line is going to sit right at the top, horizontal again. And here, a horizontal tangent line again, yes? So at least at A, C, F, and H, the tangent lines are horizontal. What can you tell me about E? I skipped over this E. What sort of a tangent line do I have there? Now, if you remember anything from 1.6, probably yelling right now at the screen saying there is no tangent line. Why? Because it's a corner. So at a corner we cannot take a derivative because there isn't just one tangent line right there. Okay, so let me start writing these down. So at A, C, F, and G, the tangent line is horizontal. Okay, before we move on even further, what is the slope of a tangent of a horizontal line? Who remembers what's the slope of any horizontal line? Again, remember the slope is the change in y's with respect to change in x's. If a line is horizontal, what's the change in y's? There's no change in y's, right? All the y's are the same. So you very well hopefully remember that any horizontal line has a zero slope. Now what does the slope of a tangent line equal to? The slope of a tangent line is equal to the derivative. So it seems to me that's an easy decision. If I want to find a maximum or a minimum, I just need to find where the derivative is equal to 0. In other words, where is the tangent line horizontal? And so the slope of it, right, the derivative, would equal to 0. What happens at E? At E, there is not one tangent line. So there is no slope because there isn't even a line. So we could say the slope is undefined or it doesn't exist. So in other words, the derivative does not exist. So it looks to me like we're looking for two situations, because it could be that your graph comes to a corner point before it moves up, right? You have a minimum that's a corner point. At a corner point, there's no derivative. Remember, a function's not differentiable at a corner point. Or where the tangent line's horizontal, we're coming to a peak, yes, whether a min or a max. We'll see how to make that distinction, but it's an easy decision. So to find minimums and maximums of functions, all we have to do is look at what? Where is the derivative equal to 0 or undefined, right? Or doesn't exist. So we're actually calling these special names a critical number. We're using the letter CN because we're not going to want to write too much. So when I say find the critical numbers, you might write CN for that. So a critical number is an x value or number at which the derivative is equal to 0 or the derivative of the function is undefined. So the derivative is 0 or undefined. And I'll write this down one more time, but it looks to me if you want to find mins or maximums, that's what you're after. A critical point, now hence the word point. What's a point? A point's not just an x, but it's the y value to it too, right? So a critical point is a point for which the x-coordinate, is a critical number. So why do I need a critical point? Because again, I might know that what? At this x value, yes, or this x value, fine, at A, the line is horizontal, so I have a min or a max, but still, where is it? How high is it? Where is that point, right? That's exactly what I was just saying. I might know that my graph might be turning at this x value, but still, how high? Where is it turning, right? Just because I know the x value, I still don't know how high I have to go to have it turn, right? The height is the y value, is the y coordinate. So I am going to need to find those special points on my graph. So how do I find the point? Well, I got to find the x first, yes? All right, so the important thing is, just as I said, that if you want to find your mins and maximums, you must find your critical points. So I'm going to say this. A min or a max, local, which again, local or absolute is a special kind of local, min or max, only can occur, so it can happen, come up at a critical point. Oh, I just said I could write CP for that. That doesn't mean that every critical point is a local min or max. So that's where you found them among. So you're going to make a list of possible critical points, but it doesn't mean that all critical points turn into a min or a max. And we're going to see those examples. When does that happen? Where you found a critical point, but it's not in fact a min or a max. Okay, so this is what we're going to do first. First practice, just find the critical points. Okay, that's the first step really in graphing such functions, in graphing your mins or finding your mins and maximums. You have to find the critical points, right? And then check up on those critical points, see which ones are mins and maximums. Okay, so how do I find a critical point? I have to look at what? First of all, find your x's, yes? So how do I find that? Find the derivative, see where it is 0, or it possibly is undefined. Again, not all of them can equal to 0, not all of them will be undefined, yes? Okay, so let's find the derivative. That's what we practiced on in chapter 1. So the derivative of this function right here is going to be a 3x squared minus 2x minus 1, right? Okay, so what do we want to do? We want to see when does this equal to 0. So I'm going to need to factor. Numbers that multiply to 3 are 3 and 1. Numbers that multiply are 1 and 1. To make the negative 2 in the middle, you have to set it just so, right? So 1x minus 3x is the negative 2x in the middle. As I said, factoring is key. So what are the two choices for x? X could equal to 1, or x could equal to, subtract the 1, divide by 3, negative 1/3. Great. So solving quadratic equations should not be the problem. Okay. So we solved it. By the way, could this expression be undefined? The answer is no. The only time when you get an undefined is when you divide by 0, right? So there is no fraction with x's on the bottom. So that's not going to be an issue here for sure, okay? So here, these two are your critical numbers. How do you turn them into critical points? Should have written it under there. I turn them into critical points by finding their y values, right? So if x is equal to 1, what's the y value to it? Well, the y value is obtained by plugging it into the function, right? That's whose mins and maximums am I looking for, not the derivative, yes? It's the function's mins or maximums, or the function's critical point. So plugging it into the function again, so 1 cubed minus 1 squared minus 1 plus 2, that's going to be a 1, right? So this is my first critical point. 1, 1. What's my second critical point? Make x equal to negative 1/3. Plug it into the function. Negative 1/3 cubed is negative 1/27 minus 1/9 plus 1/3 plus 2. Put that in your calculator. I know I found it already. The answer is 59/27. Again, put it in your calculator. No problem. So here are your two critical points. So if a min or a maximum, if you have a min or a max in this function, that's where you'll find it. Okay. All right. So let's see, I got two more and then we'll move on. Same thing, let's find the critical points. Well, without much writing, let's find those critical numbers first. And we do that by finding the derivative and then setting it equal to 0, right? Again, this won't be undefined. I don't see a fraction with x's on the bottom. So to solve this equation, sure enough, again, factoring. Factor out the greatest common factor of 4x, right? There's a 4 in common and an x in common. Can we split this up some more? Definitely. That is the difference of two perfect squares. That's how it factors into. Okay. All right, so what are my three solutions to this cubic equation, right? A cubic equation will have three solutions. 4x is 0 if x is 0. That's an x equals to 2. And again, x plus 2 is 0 if x is negative 2. So here are my critical numbers. Okay. What are the critical points to this? No problem. I'm going to take each one of these values and plug them into my function. So that's going to be 0. If you plug in a 0 here, you'll get a 3. Okay, let's plug in the 2. If you plug in the 2, 2 to the 4th is 16, minus 8 times 4 is 32, so negative 16 plus 3 should get you a negative 13. And finally, the last one is negative 2, and then again, that's a positive 16. Still minus 32 and then plus 3, that should also again be negative 13 value. So at both these x's, you are the same height in the graph. So here are your critical points. So if you have a max or a min, that's where you'll find it. Okay. And finally, one more, and then we'll take a break on this video. So let's find the derivative of this function. Well, that's a 2/3 that's coming up front. X plus 3 to the 1 less than 2/3. So again, what's also important, as you see, is that we have what? We know how to take derivatives, right? Plus, on top of all the algebra, you should already know as well. And what's the derivative of negative 5? That's 0. Okay. Ooh, what else? What's happening here? And what am I telling you every single time? What I'm telling you is that when you see negative exponents, you better fix them. And as I promised you in chapter 1, when this happened, is that it's going to become also super important in chapter 2. It's going to help you. So, what am I looking at? I'm looking at when is this derivative equal to 0. The thing is, for this fraction to equal to 0, the only way a fraction can equal to 0 is if the top is 0. And one other way of looking at it, if you want, is that you could multiply, cross multiply, yes? And what you're going to get simply is that 2 must equal to 0, but of course that's not possible. So all I'm telling you is that the only way a fraction could ever be 0 is if its numerator is 0, right? But its numerator is 2, and 2 will never be 0, okay? So the fraction won't be 0. Good, I have a second choice. What's my second choice? Can this derivative now be undefined? Yes, this derivative is undefined when it's a fraction. Yes, this derivative turned into a fraction. When does a fraction ever equal to undefined? A fraction's undefined if the bottom of it ever becomes 0. So, again, it's 0 if the top is 0. It's undefined if the bottom is 0. Remember, what is 0 divided by 7? Well, that's 0. What's 0 divided by negative 11? That's 0. But what is 7 divided by 0? That's undefined. Right? What is negative 11 divided by 0? That's undefined. So you can't have zeros in the denominator of fraction. But if the top, and by the way, 0 over 0, where does it go? It goes to undefined. You can't divide by 0 no matter what. Okay. All right. So, when is this equal to? You can divide by 3, cube both sides, but the point is really easily that at negative 3 is where your bottom becomes 0. If you plug in a negative 3 here, yes, that will make the bottom 0. So that's your critical number. I don't have much space, but I do right here. Let's find the critical points. How do I find the critical points? I plug negative 3 into the initial function. Good thing, because if I plug it into the derivative, I wouldn't find an answer, right? So, but it's the function itself. So if I plug in negative 3 into this function, what do I get? I'll get a 0 to the 2/3. That's still a 0. 0 minus 5 is a negative 5. That's possible. So just because the derivative was undefined at a point doesn't mean the function itself wasn't as well. So we'll stop this video here and we'll continue on more next time.